Let's continue with our lecture on mathematical method. This is a part of course PH3103 at IISER Calcutta. We have looked at the various aspects of the linear vector spaces. Let's move on. We were looking at the linear vector spaces and some of their important properties. Here we look at the square integrable function or L2 function. Let f of x be a real valued function in a closed interval a b. It is square integrable if integral from a to b mod fx square f of x is finite. That is what we call is a square integrable. Of course, real means f into f. It is always a positive definite. Otherwise, finiteness can be a bit of a tricky issue. So we need a positive definite function. Of course, we can define this for the complex valued function too, and in such case we'll have to replace f, or the meaning of f square becomes f into complex conjugate of x, which again become a positive definite, and this function value have to be a finite. That is what we call is a L2 function. In addition to this, sometime we may also define a weight function which is included and as a function of x in the integral. It is also useful to have weight function sometime and make this integrable finite. So that is what we call as a square integrable function, but we also have this closed interval from a to b. Both of them or either of them can take the value of infinity. That means we can have a function from minus infinity to plus infinity, or minus infinity to b, or some value a to plus infinity. All the combination can happen including infinity, and even then if this function is finite, then we call all such functions are square integrable function. A quick example, f of x is equal to 1 by x, definitely not square integrable in the interval 0 to 1, because 1 by x blows up at x is equal to 0. So the value, it's a closed interval, so the value of the endpoint also matters. So from 0 to 1 in the closed interval, this function is not square. Same function f of x becomes a L2 function in the interval 0 to 1 if we take the weight function f of x to be x squared. So this is where carefully chosen weight brings in the more features of the L2 function. We have a function sin x which is square integrable in the interval minus pi to plus pi. Of course, we can continue with this. There are a whole lot of functions which are square integrable. That is what we are looking at. Of course, this is not a new emoji. It is just that happen to say that dot 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 go on to infinity. F of x is equal to tan x. Is it integrable? Non-integrable? Yeah, you can answer it on your notes and say what is it integrable. L2 vector space. The reason for interest in the L2 function, it is that they form a vector space. Set of all L2 function form a vector space with the L2 inner product given as a phi dot psi in our notation of the vector, or in the bracket notation psi dot phi equal to integral a to b phi of x psi of x dx. That is what we call is a dot product of the two vectors phi and psi. Now, since they form a vector space, we call them these function as an element of vector space. It is called the Hilbert space. So we got to check this out, and let's start with our basic two operation. One is multiplication by a scalar, and other is adding of two vector also leads to a vector, that is, they are closed under the multiplication by scalar and closed under the addition. If phi is an element of L2, then alpha, a number, the psi equal to alpha into phi, is also L2. Of course, multiplying a L2 function by a number which is finite, still the integral in the interval a to b would still remain finite, and the function psi, which is alpha times psi, is also finite. That implies that the function is psi is also the element of L2 vector space, so it is closed under the multiplication by a scalar. Let's look at the what we call is the addition of two vector. Let phi and psi be the element of L2. Then let's define the chi equal to phi plus psi. So we have to show that that is also member of L2 space. Phi being a member of L2 space, the integral would be finite, and psi being a element of L2 whose integral or dot norm is also finite. That we have to show that the chi square, that is the integral a to b, phi plus psi into phi plus phi, is finite. So we expand this, then we know that this is already finite because psi is a member of vector space. This is also finite coming from this. The product of a two finite function, when it is integrated, would be also finite, so that makes it this is finite too. That means that psi square is finite, and it is closed under the addition operation. So we see that it satisfies the condition of the vector space. So L2 under the L2 norm forms the linear vector spaces. We also call it a Hilbert space. Hilbert space can be a general in the sense that it can take a complex number too. The same way L2 function also can be defined on a complex number. So it allows all kind of freedom. So I interchangeably use the word L2 and Hilbert space. Let's consider the dimensions of the L2 vector space. What is the dimensions of the vector L2 vector space or Hilbert space? We have been always told that it is infinity. Hilbert space is a smooth, continuously varying vector space with the infinite dimension. That need not be dimension of the Hilbert space depending on how it is constructed. It can be finite or it can be infinite. So let's construct a Hilbert space with the following definition. Let f of x be the functions, square integrable of course, expressed as sum I is equal to 0 to n, m to the n, x to the power n, where m of n is an integer and n is greater than 0. Now we see that it kind of forms a Hilbert space in the interval 0 to 1. This made up space has some interesting property. If n goes all the way till infinity, then the dimensions of this vector space becomes infinite, or it's an infinite dimensional vector space. On the other hand, we can restrict n to be n modulo, where n is some integer, then we find that it is a finite dimensional vector space. Modulo n is basically you restrict the number from 0 to capital N minus 1, so that whenever it exceeds, you take divide it by capital N and use the remainder. For example, you can arrange them nicely on a clock-like thing, that where you have a 0, 1, 2, and 3. Whenever you add two numbers, let's say 1 and 3, you becomes 4, and then that becomes 0. So 2 into 3 is 6. 6 becomes 2, because 6, when you find the remainder with 4, it is 2. So that way you form a finite this thing. Then you have a finite basis h to the power n. Then this vector space becomes finite. So this is an example of finite dimensional L2 space. So this is an ad hoc constructed, may or may not be useful. Let's continue. Linear independence of vectors in the Hilbert space. Let's look at the linear independence. Let two elements phi and psi are functions in Hilbert space. How do we show they are linearly independent? Of course, you would say that alpha into phi plus beta into psi should be equal to 0 if and only if alpha is equal to 0 and beta is equal to 0. No, this won't do, because this is a definition. You are stating a definition, does not say how to figure out that this combination goes to 0 if and only if alpha is 0 and phi is 0. We have to have some method to calculate it. In the case of Rn, we know that when we arrange them n vectors, when we arrange them as a row, either as a row vectors or column vector, and the determinant is 0, mean that they are linearly dependent. If the determinant is non-zero, then there is no way to express one in terms of another, and we say that they are linearly independent. It can be shown exactly, but we are not really interested to show it. Let's see in this case how to do it. Now let's first differentiate this combination. Alpha is constant, so when we differentiate, we get alpha phi prime into beta psi prime equal to 0. Here prime means the differentiation with respect to variable x. Now we call the first equation, the linear combination itself, as a and its differential as b. Now we say that psi prime into equation A subtract phi into equation B, and that is equal to 0. Explicitly put in, what we get is a phi into psi prime minus phi prime into psi prime. Now we can clearly see that either alpha equal to 0 and beta equal to 0, or this combination phi psi prime minus phi prime psi equal to 0. So this comes to the Wronskian and linear independent. Let phi and psi be the two functions. Well, in Hilbert space, it need not be in Hilbert space. It can be in general any two function, but the linear independent doesn't make sense in general. So we say that they are functions in Hilbert space. The Wronskian phi and psi is equal to phi into psi prime minus phi prime into psi. The previous results, which we have seen explicitly, two functions phi and psi in a Hilbert space are linearly independent if and only if their Wronskian phi and psi prime minus phi prime psi is not equal to 0. Let's look at the quick example. We take function, let's say phi is equal to x and psi is equal to x square. Their Wronskian is basically x into 2x minus 1 into x square, which is not equal to 0. That means x and x square are linearly independent. We know that there is no way to produce x square from x. Of course, in the linear sense, that if you multiply x with itself you get x square, but that is not allowed in the linear vector spaces. In the linear vector spaces, by taking no linear combination of x, you can reach to x squared. That means multiplying by some constant. Phew, there we show that they are linearly independent. Now the next question is, do they form the basis? Wronskian and linearly independent idea can be extended to n functions. The n can be infinity. Let phi of I be n elements of Hilbert space. They are linearly independent if and only if the Wronskian of phi n element is given as a determinant of phi, phi 2, phi 3, phi n as a one row. Second row is a first differential of a whole set of function, and then second row is second differential till all the way nth differential, actually n minus 1, n minus 1, n minus 1, n minus 1 differential of all function. Phi n here, upper index stands for nth differential with respect to x, and the lower index I stands for its position in the n system. So the functions are linearly independent, then their Wronskian is non-zero. There is one more error. Let's look at the functions x, x square, x to the power 2 and so on, x to the power n. Are they linearly independent? Well, you can check it on your own. The algebra is large to determine the, we have already checked for n is equal to 2. You can check it for higher n's and satisfy your own curiosity at your own cost. We will continue with the more aspect of Hilbert space in the next lecture. Let's stop here.